Hi, I'm Jeff Beer, founder of the Edge AI and Vision Alliance and program chair for the Embedded Vision Summit. I'm very excited today to be speaking with Professor Trevor Darrell of UC Berkeley. He'll be giving the opening keynote talk at the Embedded Vision Summit on May 21st in Silicon Valley. Professor Darrell, I'm really looking forward to your Embedded Vision Summit keynote. Thanks very much for making time to talk with us today.
Thanks for having me.
Your research group has produced really a tremendous amount of influential work in AI and computer vision. For those who aren't familiar, how would you summarize the focus of your group's recent work, especially as it relates to computer vision and other forms of machine perception?
Well, machine perception's undergoing a revolution right now. It's being transformed by large language models. And the technologies that we're using are becoming more universal. There's no longer a substantial distinction between the technology for computer vision and the technology for natural language processing and even the technology for robotics. So we're seeing multimodal LLMs that are able to process images, refer to elements and objects and scenes, analyze them, reason about them, give answers. It's incredible the progress that we've seen by combining large data, large compute, and large models over the last 5 years.
Yeah, really stunning. And to maybe put that into kind of practical terms for folks in our community who tend to be very focused on applications, bringing these things together, what kind of capabilities is that enabling for the first time?
I think the main um, point of leverage with regard to prior capabilities, we've had strong machine learning and computer vision now for a decade, and even weak computer vision for 2 decades. But what we haven't had is sort of common sense, both in terms of the robustness that that provides to models, even at the edge, and the controllability that that provides to models, either in training or deployment. And I think there's lots of implications and applications of that. For example, I think we've had machine vision for inspection systems for a long time. Is the part coming down the line? Even before machine learning, we had architectures for that. Machine learning made it more powerful. Deep machine learning made it even more powerful. But if someone happened to put a ham sandwich on the line, the ham sandwich moved down the line. I was once involved in consulting on a project which was trying to count poker chips on a poker table, or analyzing intellectual property in that space. And literally, if you put a ham sandwich on or a certain kind of sandwich made with sliced tomatoes, it would think it was poker chips and count them as poker chips. And so, you want a system that knows when you put something completely out of domain in front of it, it say, hey, there's something wrong here. There's a pink elephant that just showed up. It's not this is not poker cards. These aren't poker chips. This is like something's wrong. We've never had computer vision systems that could do that, and certainly not do that in a cost-effective manner in the edge. That's, I think, what we are about to have or already have in our contemporary systems in 2025. So they're much more robust and can kind of tell when there's something unusual going on. And then further, they're controllable in the sense that previously you really had to train a system with lots and lots of examples of the specific type that you expected it to see in the environment. And sometimes you could train the system in simulation, or translate training data from a related domain. But yeah, it was just burdensome. Or maybe in the old days, you would manually code logic, which would always be brittle. I think now we're increasingly going to train our systems in natural language and teach them the way you would teach a human being to solve a task. So that's what I mean by they're much more controllable or much more accessible. And I think that will have incredible implications both in training and in deployment when you want to maintain, refine, or correct a system.
Yeah, when we do our annual survey of product developers who are building all different kinds of devices and systems out in all kinds of industries that are incorporating computer vision and related technologies, consistently the top pain points that they report relate to training data, obtaining the training data, labeling it, cleaning it, managing it over time, et cetera. So the idea that we may be able to really dramatically reduce the reliance, our reliance on having to do that at such large scale, hundreds of thousands, sometimes millions of training images is super exciting. So can you tell us a little bit more about this? Like, how is it merely a matter of, oh, we have a model that understands natural language and understands images, and so we just tell it in natural language what to look for because it's been trained on sort of vast, diverse pairs of captioned images, essentially text plus images, or what's going on here? How does this work?
I mean, I think the answer to your question is closer to yes than no. I mean, that is what's happening, and maybe you're not going to see that immediately in at the edge, but what you are seeing is auto training systems that can almost replace humans. And of course, even humans need training data. If I hired a brand new person to come and do something in my garden or my auto shop or even in my house, they don't get it right the first day. You have to manage them and teach them. And that's usually through multimodal instruction, right? So I think you're always going to have hundreds or thousands of training examples for any task, or dozens. But some of the training might be in natural language and some of them might be in visual examples. And if it's a really a really experienced human probably has 10,000 examples of really trying to get something right. So we'll still have that, but you won't need the level of training data that we've needed in the past to just get basic competence. That seems to be coming zero shot out of the box from models such as you were implicitly referring to CLIP models or state-of-the-art multimodal large language models that are derived from representations similar to that. They're just sort of working. If you want to say, is there a horse standing on top of a school bus? They can tell you if it's true or not. The base competence has already been learned. And again, through a paradigm of massive supervision, it's an open research question that many of us are very excited about. Could that have learned even without the massive supervision on the web? Obviously, humans evolve without learning vision from internet training data. Probably the answer to that would be yes, eventually. But whatever, today we have that as a base capability, and computer vision and robotic vision systems are going to exploit it in the future.
Yeah, very exciting. And I think one of the domains where this has tremendous potential is robotics. And I remember that a few weeks ago, you were kind enough to give us a tour of your lab, and there were a lot of robots around. And I think you made a comment along the lines of robotics and computer vision are essentially now the same thing. Did I hear that correctly? And could you elaborate a bit on that?
Well, I'm old enough to remember when they were the same thing. When I started as a graduate student in computer vision, the first textbook that I ever had was from Berthold Horn, called Robot Vision. And you can go back and see what the picture on the cover of that textbook is. It's a very creepy looking humanoid robot staring over the cover of the book to you. So robotics was front and center, and basically computer vision and robotics were not distinct prior to 2000. And then starting in the 2000s, internet vision became a dominant aspect of computer vision, and maybe computer vision diverged from robotics substantially for 2 decades. I think it's coming back. It's coming back because the methodologies are increasingly identical. Natural language processing, computer vision, and trying to act in the world were previously thought as 3 very different fields with different methodologies, different histories. Again, unless you go way back to, again, the 80s and the 90s. But now the paradigms are unifying. And I think, at least in terms of research computer vision, because of the success of the models that we just described, the current research challenges are really in how we can perceive and act and do that at scale. That hasn't been solved by industry yet. And so, as a research matter, I think many of the cutting edge topics in computer vision are now really intertwined with natural language processing and robotics, um, more so than not.
Very interesting. Now, earlier you touched on being able to do these things efficiently at the edge, and that obviously also ties in with robotics because robots are at the edge. Um, and I see that in your keynote abstract, you're planning to talk about techniques to overcome obstacles like the massive memory and compute requirements associated with today's state-of-the-art models. Um, how would you characterize where we are today in terms of current state of the art and the trajectory in this vein? Are we talking about conventional approaches like a distillation and model pruning, or something else?
I think all of these things are happening and going to be very successful. I mean, it feels a little bit. Again, I'm such. I don't want to say I'm such an old timer, but sometimes I feel like that. I remember the early days when MPEG compression was a piece of software that you would run on a compute, general purpose computer, and it would take a significant number of seconds per frame sometimes to or for a short video. And now it's all baked into hardware, and obviously everyone knows how efficient that is. So I think we're going to see the same revolution over the decade that's coming with LLM inference. I think the idea that it's expensive to run an what we consider now a large LLM, there will be hardware, there will be analog, there will be distilled implementations. I'm not sure I want to point to any single revolution there. I think that's the history of engineering in Silicon Valley, that it's several simultaneous, orders of magnitude that get chipped away at a problem over a decade, and suddenly you have a 4 order of magnitude more efficient model. Just look at the power of today's open source models for LLMs, multimodal LLMs, versus 2 years ago. And today's open source models basically match last year or the year before's closed source models. And everybody thought that was going to be impossible. And we're talking a 5x or 10x improvement on many metrics in certain cases. So I still feel like I'm really an optimist in terms of many things becoming cheaper and faster and better. I still think many of these problems still don't fully work. We don't always know how to get the user in the loop with AI. Some things are trivial with an interface like ChatGPT or Gemini or Claude. And some things it doesn't seem to yet work. It's the classic, in previous decades in AI, we knew that we learned how to solve chess very quickly or Go, but we're still not so sure how to pick up the chess pieces and put them on the chessboard. And I think there's still some places in the AI world where the model may be super smart, but it still can't figure out what to do that actually helps a user.
Yeah, and that reminds me of another theme that's mentioned in your keynote abstract about using LLMs as visual reasoning coordinators. That's an intriguing idea. Can you comment on that, and how does that relate to this kind of frontier of what's possible that you just were talking about?
Well, now multimodal LLMs, that it's been clear for 6 months or a year, both with multimodal LLMs and regular LLMs, that it's not just scaling training data. It's not just massive amounts of training data, but you actually now need some smarts at inference time, and you need to train that at some level, but also have structures where models can introspect, can apply chain of thought reasoning. If I want to see whether all the cars are parked in a parallel parked properly in a certain parking lot, well, I want to find all the cars. I want to look at the orientation of each car, and I want to assess whether those orientations are consistent. We can train that as a single feed forward pass convnet or transformer. But if we want the most general processing, and tomorrow I change the problem statement just a little bit so it's not, are they all aligned? I'm like, is the sun shining on them in a certain way? And is there a trash can next to the front door? You don't want to try and pre-compute the power set of all attributes in your environment as a set of classifiers or features. You want a system that can deploy elements, deploy sort of constituent elements of understanding in a compositional way. And that's often referred to now as agentic computing um, or visual reasoning. There's several different buzzwords in the field. I don't care which one we use. I think that general paradigm is going to increasingly be important. And then once you find a certain skill that you've reasoned through, figured out how to do it, if you then are told, I have to do this every day, every morning for the next 1,000 days, you're probably going to then distill it into a feed-forward network. And that's the sort of cognitive reflex, system one, system two, or thinking fast and slow story that many of us know and find appealing.
And are these like compositional or heterogeneous approaches? Do they also help to address the resource requirements and therefore help make it more feasible to implement these kinds of intelligences at the edge?
Yeah, it does seem like these architectures for agentic reasoning can often be deployed at much smaller scale than the brute force, let's do everything at training time regimes.
Yeah, very, very interesting. Now, your research group has really been a powerhouse and produced so much influential research, but I know you've also been involved in quite a few companies over the years, and I understand that you recently co-founded a startup. Could you tell us a little bit about what that startup is doing and how it relates to these themes we've been talking about?
Yeah, I'm very excited about a startup that I've co-founded with several of my former students called Prompt AI. We recently came out of stealth and announced our first product called See More. It's both meant to refer to the fact that we're seeing more in an environment, but also it has a name, See More, like a first name. And it's helping everyday people in their home or wherever their environment is to interpret their visual world and the cameras that they have in the world. We integrate with a number of different Wi-Fi camera providers and grow that list in the future. And we enable persistent agentic multimodal LLMs like ChatGPT, Gemini, and the like, both open source and closed source. We enable users to leverage that power in understanding their environment, deliver notifications and analysis of camera feeds that are much more useful than the current state of the art.
Very interesting. And if people are interested in trying this out, is it publicly available today, or is there a way for people to get access to it?
It's just out on the iOS App Store, and look to Prompt AI or See More.
Very cool. Well, Professor Darrell, based on what I've heard today, I really can't wait to hear you delve deeper into these topics in your keynote talk at the Embedded Vision Summit on May 21st in Silicon Valley. Thank you so much for taking time to talk with us today.
Thanks, and I'm looking forward to the event.